So welcome back to the RAMSuite today. I just wanted to start showcasing one of the modules. I'm going to be looking at uptime today, so really focus on availability analysis. There is quite one of the simple tools that I built quite early on, which is a simple parallel package modeler. So if you've got a n out of or m out of n type scenario and you want to work out what the overall uptime of the system might be given some downtime failure information related to the child components, you can use this tool. Today I'm going to focus on using the RAM modeler and showcase it with one of the models that can be drawn out from the database attached to this tool. So this is just a SQL database at the back end where all the RAM models are sitting. Again, this usually takes 2 seconds, so sometimes the development server really just doesn't cotton on when you start up. Not sure why. So there's a bunch of tables here that are served up. You've got equipment index, subsystems, your system compilation, equipment, failure modes here, failure mode responses. So basically, does anything happen automatically when a failure occurs? Inspection, condition-based maintenance, time-based maintenance, inventory, so min, max levels, lead times, that sort of thing. Task lists, so what components are actually used for specific maintenance tasks. A whole bunch of other inputs that I haven't really worked on too much yet. So you can generate a reliability block diagram from a loaded model if you want. What I'm just going to show you while I'm here as well is that there are a whole bunch of APIs that I've set up so that you can access the database. So here you can see all the tables in a given RAM model if you know the RAM model ID. You can also go for particular tables. So let's go back and let's try model/detail/equipment. Okay, so you got your equipment there, and you can get it in different formats if you want. Yeah, so that's basic JSON format there, or HTML if you so desire. And so there's a whole bunch of different tables. So you've got equipment, you've got subsystems, what? Maybe it's subsystem structure. Yeah, okay. I can't remember exactly all the APIs that I've created, but there's a whole bunch there that you can access. Anyway, okay, so this is the RBD representative of that system. Pretty basic RBD. You've got some elements in series, some of those elements then in parallel, and then an overall system. I'm just going to go back and I'm actually going to run this RAM model just so you can see the type of outputs that you get. So let's run 10 simulations and let's run it for 10 years. And so I've set up a lot of these modules as asynchronous tasks, which means that your browser is not disabled. Like you can keep using the app to do other things while that task is running. So this is all I really need to know, which is the task ID. And then I can open up my browser and get the status of that task at any time. And once that task is complete, this URL is going to reroute me to the result. So I think that's pretty cool. Like I can go away and do other things. I could run another RAM model in the meantime if I wanted and just record this task ID, and I can come back to it later. So it's kind of set up for really freeing you up, cloud-based. Yeah, pretty happy with it. Yep, just working through that simulation and then the processing of the results. And again, if you enhance the resources, associated with the machine that's running this, like give it 4 gigs of RAM instead of half a gig, a lot of these processes would be a lot faster. So what you see here is that you just got some timestamps on how long that simulation actually took to run. You get a production performance, so basic distribution of the production performance. You can actually see there's quite a high standard deviation in the uptime. So there's almost like 1% standard deviation in the uptime. If this was formatted properly as percentages, and you can see some of these min values over here. So that's not great, this particular model. And it's also maybe a product of the fact that I only ran 10 simulations. But if we have a look at the node criticality, for example, this tells you what percentage of the overall system downtime was associated with a particular node, or if I rephrase that, if this node operated perfectly, what percentage of production uptime could I sort of regain? So of that, what do we say the mean production uptime was? The mean production uptime was 99.2%, so there's a 0.8% downtime. And of that 0.8% downtime, if this pump impeller failure mode wasn't there, we would basically get back half of that 0.8%, so 0.4% uptime increase. If this failure mode wasn't there. So obviously these pump impeller failure modes are the ones that are really governing our causes of downtime. Like I say, this impeller failure mode is related to this equipment, so that's why this equipment also has a high percentage of the downtime, or a high criticality. And this pump is a child to this pump package over here, which is also why it has a high percentage of criticality and so on. So I guess if we really follow it back to the root cause, it's talking about these pump impeller failure modes. So then let's have a look at those pump impeller failure modes in a bit more detail. Right, so I guess I've got 4.8 downtime events per simulation on average. So it could be the frequency of events that's causing a higher loss attributed to those nodes. But also, if I actually look at the mean downtime, I can see that for this failure mode, the mean downtime was 31 hours, and for this failure mode, the mean downtime was 89 hours. So there's something causing a big swing in the mean downtime. And what I'm thinking, if I look at you can confirm that, I guess, looking at these maintenance tasks, that the replacement of the pump probably should take something like 30 hours, but instead the pump replacement is taking 106 hours on average for this task. And if I try and understand why that is, now looking at inventory, if I look at this pump assembly, what we're seeing is that we're seeing some stock out events, so when stock is drawn down to 0, and we're seeing that these stock out events are resulting in a maintenance delay being caused on average of 367 hours. So for all the times that maintenance delay did occur, that's the average maintenance delay. Maintenance delay may not have occurred many times, so maybe that's not the best representation of what's happening with the materials, but basically the stock out event's happening, it's causing maintenance delay. So if I really wanted to reduce the standard deviation or bring up the lower bound of this production performance, what I'd be doing is I'd be looking at my minimum stock levels for this pump assembly, and maybe increasing my minimum so the reorder point, or increasing the max and increasing the initial stock held. You can also go into details by simulation. So I don't know which simulation it was that the stock out events were occurring in, but that's something I can build in later. But if I was to actually look at these specific simulation details, I can go and have a look at the inventory lifetimes, for example, and I can see that for material 1, stock was drawn down to 0, like at the end. So there was one stock out event for this simulation for material 1, which is the pump assembly, right at the end of the simulation. And yeah, I can kind of like dig into those details and validate them if I so wanted to. You also get full event logs. And yeah, so that's one of the modules I've been working on, which is the RAM Modeller. And I just wanted to share that. Stay tuned for more if you're interested.